Okay, so this is going to be the answer key for that question at the end of the last video. If you haven't watched that yet, go ahead and watch that first, and maybe look at that last screen and think about that as we go through solving this. So look at that last screen and you'll see where we're getting the information from that I'm writing down. So I'm going to be making a table here because we have two things. We have water and we have iron. Again, this is on that last screen from the previous video. And if we read through this, we see we have an 84.55 gram sample of hot iron. So I'm going to write this in our table as 84.55 grams under iron is dropped into a 100 milliliter sample of water. So I'm going to write 100 milliliters of water over here. Now we're going to have to think about what to do with this information because the heat equation does not have anything about milliliters in it. It doesn't include volumes. So what we need to do is we need to somehow take that 100 milliliters and convert it to units of grams. Now this is water, and we know that for water that 1 gram is equal to 1 milliliter. So we can say that we have 100 grams of water. Now we can only do this for water. We cannot do this for anything else where we can take the volume and immediately say it's the same as the mass. Okay, this only works for water. The reason I wrote it in this way in the question is because when you do your lab, this is exactly how you're going to measure the water. You're going to measure a volume of water. You're not going to measure a mass. And you're going to use that volume and assume it's the same as the mass. So this is why we're doing it in this way on this problem. So a 100 ml sample of water at an initial temperature of 19 degrees Celsius. So let's go ahead and write that down. So the initial temperature of the water is 19 degrees Celsius. So what I'm writing there, this is T with a subscript of I for initial temperature. And then the final temperature of the water is 24 degrees Celsius. What was the initial temperature of the iron sample? I'm going to go ahead and write over here Ti is equal to question mark. That's what we're trying to find. Now before we can do too much more, there's some missing information here. So let's think about what we're trying to do here. What we're trying to do is we're trying to say the heat gained by the water is equal to the heat lost by the iron. Okay, that's what we're trying to do. And we know for this equation we have a heat equation, so mass of the water times heat capacity of the water times delta T of the water is going to be equal to negative mass of the iron, heat capacity of the iron, delta T of the iron. So that's what we're trying to do. We're trying to do something with this. This heat equation is equal to this heat equation. So in our table, we want to make sure we have enough to do that. So we have, let me go ahead and write mass over here. So we have mass of water, mass of iron, enough to do delta T over here, not quite enough over here. So let's think about what else we need to have here. One thing we need to assume is that the final temperature of the iron is the same as the final temperature of the water. So we're going to say that the T final is the same for both the water and the iron. And the idea here is that we wait long enough that when we measure the temperature of the water, it's the same as the temperature of the iron. Okay, so that's what we're doing when we write that. We also need to have these heat capacities. So what we would do is we would look those up. So if you look up water, it's 4.184 joules per gram degrees Celsius. If you look up iron, it's 0.449 joules per gram degrees Celsius. So we're looking these up on tables. Now depending on which metal you're using, you could have a different number here. If you're using aluminum or copper, your heat capacity will be different. So just be aware you're going to have to look that up yourself. So what we're going to do, we're going to take this equation, and we now have everything except for one piece of that equation, and that piece is going to be part of this bit over here, this delta T of the iron. So I think the best way to approach this is to maybe solve for delta T of the iron and then take that and do some additional calculations. So what we can do, we can divide both sides by mass of the iron, specific heat of the iron. Mass of the iron, specific heat of the iron. So these will cancel out. And then I'm going to just switch sides here, so we're writing it like this, starting with our unknown. So negative delta T of the iron is equal to, and then we put in the numbers, we have 100 grams for the water. We have heat capacity of the water, and we have delta T. Actually, you know what, I haven't calculated that yet. Let's go ahead and do that over here. So delta T is equal to the final minus the initial. So T final minus T initial, so that's 24 degrees Celsius minus 19 degrees Celsius. So we have delta T is 5 degrees Celsius. So we'll put that in over here, 5 degrees Celsius, and then that is divided by the mass of the iron. We had 84.55 grams, and then specific heat of the iron is 0.449 joules per gram degrees Celsius. Okay, so that's for the delta T of the iron. So if you look at the units, the grams will cancel, joules will cancel, these grams will cancel, the degrees Celsius cancels, and we'll have units of degrees Celsius, which are the units we want. If we do the math here, we're going to end up with 55 degrees Celsius, and that's negative delta T of the iron. Just one thing to notice here, we technically have one significant figure, so just be aware of that, and usually what we would do would then be to round when we get our final answer, especially in this case because we have, as we'll see, we'll be adding that to something. Okay, so let's figure out what to do with that. So the delta T is equal to T final minus T initial, and in this case we have negative delta T. So we're gonna what we can do is we can say, let's just go back a step. So let's say delta T is equal to negative 55 degrees Celsius. So that will make it easier to put that into this equation. So this is for the iron. What we want is the initial temperature of that iron. So what we're going to do is we're going to say that the T initial is, we'll do negative T initial, so we're just adding that to both sides, or subtracting that, I should say. So T delta T of the iron minus the final temperature, and if we switch the signs there, so we have T initial is equal to T final minus delta T of the iron. And then we put in the numbers. T final was the 24 degrees, so we have 24 degrees Celsius, and then we have minus a negative 55 degrees Celsius, and we do the math, we get 79 degrees Celsius. Now I want to talk a little bit about what this double negative means. The reason why we have this negative sign is because, remember, heat going from one is going from one to the other. So we have a negative sign to show that something is losing energy, something else is gaining energy. And we want to think about, because of all of these negative signs, does our answer make sense? And let's actually go ahead, we should call that 80 degrees Celsius for the sake of significant figures, because we have one over here. Let's think of that, if that number makes sense. The number will make sense if the final temperature is between the initial temperature. So if we have an initial temperature we're saying now is 80 degrees Celsius, we have, this one is 80, this one is 19, and then the final is 24. So the final should be between the initials for the water and the initial for the iron, and that's what we have. And then it is closer to the temperature of the initial temperature of the water than it is to the initial temperature of the iron, and that's based on the difference in heat capacity. Okay, so we would expect that as well. So that is how we solve this problem. I'm going to try to leave it here so most of that is on the screen here at the end. So as you are going through this, if you want to kind of leave this up at the end in order to have something to reference as you're solving your lab, feel free to do so.